To multiply rational expressions, we want to look at how we multiply numerical fractions and make sure that we follow the same rules that we use for multiplying numerical fractions when we're working with the algebraic fractions. The reason is that when we deal with our algebraic fractions, they really are just expressions that have variables in them that take the place of numbers. So we want to make sure that the structure of how we deal with the problems remains the same as what we did when we had numerical fractions. So in each of these segments with the rational expressions, I'll do a recall segment on what we did with our numerical fractions before going to the one that's the algebraic ones. So let's recall how we multiply two numerical fractions. Remember, to multiply fractions, we just wanted to multiply straight across the numerator and straight across the denominator, but we always wanted to leave our answer in simplified form. Now, to simplify a fraction, we needed to write all the factors of the numerator over all of the factors of the denominator so that we could see how to remove the common factors between the numerator and denominator. Well, in order for us to take advantage of the fact that when we're multiplying, it's the same operation that we need of the attachment when we're removing our common factors, then to actually set up to get ready to do this problem, we're going to write the multiplication across the numerator and across the denominator. So we have 12 times 75 in the numerator and 9 times 20 in the denominator. But we're not actually going to carry out the multiplication and get a larger number that we'd end up having to refactor anyway, because the attachment is already times. We already have a partial factorization of it that we can use to our advantage. And the same thing in the denominator. So what we want to do then is we want to look at saying, well, the attachment is already times. Let's go ahead and complete the factorization of each of these individual factors. 12, if I go down to prime factorization using the prime factor tree, is 2 times 2 times 3. And then it's times 75, and we'll just go ahead and review that. If I do the prime factor tree for 75, well, 75 is 3 times 25. 3 is prime, and 25 is 5 times 5, where 5 is prime and 5 is prime. So I'll replace 75 with 3 times 5 times 5. And you would have done the same thing with 12 also. I just didn't write that one out. Now in the denominator, my first factor is 9. Its factorization done to prime factors is 3 times 3. And then times, and if I do a prime factor tree for 20, we'll get that it factors down to 2 times 2 times 5. If you wrote 4 times 5, you just didn't go all the way down to its prime factors. Okay, now I've done the prime factorization of the numerator and the prime factorization of the denominator. So since it's all attached with multiplication in the numerator and denominator, I can go ahead and remove my common factor pairs. I have a pair of 2's that can be removed, another pair of 2's that can be removed, a pair of 3's, another pair of 3's, and a pair of 5's. So when I look at what I have as far as the final simplified answer, I have a factor of 5 in the numerator, and in the denominator, all of my common factor pairs removed from that. So 5 in the numerator over 1 in the denominator leaves me a simplified answer of 5 for that multiplication. So this just comes out to be 5 over 1, which is 5, if we want to write it in its simplified form. Well, we want to carry this idea over to the next example. Notice I have a multiplication that's between two fractions. The thing that's different about this is that I have more than one term in my numerator and more than one term in my denominator in certain cases. Well, when we have that, we have to remember that the length of a fraction bar is a grouping symbol. So if I'm writing this all as my multiplication with one fraction bar, I have to remember that any numerator with more than one term, I have to grab as an open the entire numerator and a close to show that that came from a numerator of that individual fraction, or also in the denominator we're going to have to do the same thing. So I'm going to write this as my x plus 3 times my 6 over my 2x plus 4 times the x squared minus 9. Now at this stage, we are right where we were here with the numerical fractions. And remember what we did was we then took each factor and we factored it the rest of the way down to its prime factors so that we could see the common factor pairs that could be removed between the numerator and denominator. That's what we want to do next here. So I have my fraction bar. X plus 3 doesn't have any common factors all the way through. It's to the first power, so nothing more will factor for the x plus 3. I'll keep that in its parentheses. The 6 factors down to prime factors of 2 times 3. And I want to do that because it's an individual factor. Now, in the denominator, the first factor has 2 terms, and it has a common factor of 2 between these 2 terms. So we'll factor out the common factor. 2 goes into 2x, x times, and 2 divides into 4, 2 times. So I factored out a common factor of 2 from these 2 terms of this first factor in the denominator. Now let's look at the second factor in the denominator. There is no common factor all the way through. It has 2 terms. It's got a minus between it, and the first term is a square and 9 is a perfect square. So this is a difference of 2 squares. It factors as x plus 3 times x minus 3. So now looking between the numerator and the denominator of this fraction, I see a common factor pair of x plus 3's that can be removed, a common factor pair of 2's that can be removed, but that's all that can be removed between the numerator and the denominator. So my result from this multiplication, writing it in its simplified form, I have a 3 in the numerator, and in the denominator we have an x plus 2 factor and an x minus 3 factor. And we want to leave that denominator factored so that if someone looks at this later on and they see at a glance, they can tell that we've written our answer to this multiplication question in its simplest form possible. And that's how you multiply rational expressions.